Welcome to The Explainer. Today, we're going to pull back the curtain on a really clever piece of networking history. It's the ingenious system that basically kept the early internet from turning into a complete and total traffic jam. So let's just start with the core problem, right? You've got a bunch of computers in a room, they all need to talk, but there's only one single cable connecting them all. How in the world do you keep them from all shouting at once? You see, in the early days of Ethernet, we're talking about old school stuff like 10 base 5 and 10 base 2, every single device on the network was hooked up to the same shared wire. Seriously, you can just picture it as one long party line for computers. Now, the problem with a party line is pretty obvious. If two computers try to send a message at the exact same microsecond, their electrical signals literally smash into each other on that wire. The result? A garbled, unreadable mess. We call that a collision, and without some rules of the road, it would make communication pretty much impossible. So, how do you fix it? How do you bring some order to all that potential chaos? Well, the answer turned out to be this incredibly elegant system, and you can actually compare it to something we all do every day. The best way to get it is to just think about being at a dinner party. Before you say something, you naturally listen to see if anyone else is talking, right? And if you and someone else accidentally start talking at the same time, you both do that awkward, "Oh, sorry, you go." You both politely stop, pause for a second, and then one of you starts again. That is exactly the logic they built for these early networks. Now, this whole dinner party etiquette has a fancy technical name, Carrier Sense Multiple Access with Collision Detection, or just CSMA/CD for short. And if you break down the name, it tells you the whole story. Carrier Sense just means it listens first. Multiple access means, hey, everybody gets to use the wire. And the real magic, collision detection, means it knows what to do when two computers inevitably talk over each other. Okay, so let's get into the nitty-gritty. Let's walk through the actual step-by-step process a computer would use to get its message out. In a perfect world, when everything goes smoothly, it's a really simple 5-step dance. First, the computer has some data it needs to send. It listens to the cable. Is it quiet? Perfect. It starts transmitting. And while it's sending, it keeps one ear on the line, just in case. If it gets to the end of its message and heard nothing but silence, success. The job is done. Easy enough. But the real genius of a system isn't how it works when things are perfect. It's how it deals with problems. So what happens when two different devices both listen, both hear silence, and both decide to start talking at the exact same moment? Well, when that collision happens, a very clear recovery plan kicks in. First, both devices blast out what's called a jam signal, which is like a loud alarm telling everyone, hey, stop, there was a crash. They make a note that their transmission failed. And then, and this is the absolute key, each computer calculates a random amount of time to wait before trying again. That random pause is called a backoff, and because it's random, it makes it super unlikely that they'll just collide again on the next try. And that jam signal, you can think of it as the network equivalent of shouting, "Everybody hold on." It's a very specific pattern that tells every other device on that wire, hey, that last bit of data you heard was garbage, just ignore it. It's a crucial cleanup step to make sure that corrupted data doesn't get processed by mistake. Now, as smart as CSMA/CD was, it wasn't perfect. It wasn't foolproof. In some situations, maybe with a bad cable or a network that was just physically too big, you could get some really weird and problematic side effects. For instance, it turns out not all collisions are created equal. A local collision is kind of normal. It's the expected result of two people talking at once. The system handles it. But a late collision, oh, that's a huge red flag. That means something is seriously wrong with the network itself, like a cable that's way too long. And the protocol doesn't automatically fix this. It's up to some other piece of software to realize a message just vanished into thin air. And this led to one of the most fascinating little quirks of the whole system, something called the channel capture effect. It's this bizarre situation where one lucky, or you could say aggressive computer, could actually hog the entire network for itself. So here's how it would work. Let's say computer A and computer B collide. They both pick a random wait time, but A just happens to pick a shorter one, so it wins and gets to send its data. Now, if they immediately try again and collide a second time, the backoff algorithm makes computer B wait for a random time from an even bigger range of possibilities, because this is its second failure. This actually makes computer A statistically more likely to win the next round. And after a few wins in a row, computer A can essentially capture the channel, firing off message after message while poor computer B is stuck waiting for a longer and longer time. So you might be thinking, if CSMA/CD was so important for making early Ethernet work, why aren't we using it everywhere in our wired networks today? Well, the reason is a massive evolution in the hardware that runs our networks. And that answer really comes down to the giant leap from using network hubs to using network switches. See, a hub was basically a dumb device. A signal came in one port, and it just mindlessly repeated it out of every other port. This created one big shared space where collisions could happen. A switch, on the other hand, is smart. It actually learns which computer lives on which port, and it sends data only to the port where it needs to go. What this means is that modern switches gave every single computer its own private, dedicated lane on the network. Think of it like going from a single-lane country road to a multi-lane superhighway. And with full duplex connections, computers can send and receive data at the exact same time. This totally eliminated the shared wire problem. And if you eliminate the shared wire, you eliminate collisions. And well, if there are no collisions, you don't need collision detection anymore. And that kind of leaves us with a final thought to chew on. While CSMA CD solved a problem that's mostly gone from our wired world, the fundamental challenge, lots of devices trying to use one shared space, is more real today than it has ever been. Just think about Wi-Fi, 5G, satellite internet. The medium isn't a copper wire anymore. It's the air all around us. The dinner party problem is still here. It's just gotten a whole lot bigger. So what's going to be the next evolution of digital politeness?